Hi everyone, and welcome to Chapter 6, Lecture 1. This is going to be on the wave and particle nature of matter. So this is section 6.1 to 6.4 in your book. And what we're going to focus on in this is the wave-particle duality. And this was all brought upon by J.J. Thomson when he discovered the electron. So he won the Nobel Prize for discovering the electron. His son actually also won the Nobel Prize for describing the wave-like nature of the electron. And we'll also talk about Heisenberg and de Broglie and some other scientists who can actually be credited for helping to contribute to the wave-particle duality theory. So Niels Bohr tried to explain the location of electrons, and what he did is he based his ideas on the relationship between matter and light. And one of the ways that light travels through space is by electromagnetic radiation. Light from the sun, energy that's used to cook food in microwaves, if you have to go to the doctor and get an x-ray, any heat from a fireplace, those are all types and examples of electromagnetic radiation. So in order to really understand the electronic structure, first we need some background information on electromagnetic radiation and light, and then we can start to discuss more of Bohr's ideas. So there are two theories that can explain light, the wave theory and the particle theory, and this is why it's called the wave-particle duality. So first we're going to look at light as a wave. So light has a wave-like nature. So when we look at the wave theory, we first need to talk about what a wave is. So waves have three primary characteristics. We have the wavelength, the frequency, and the speed. We can also talk about the amplitude of a wave, but we're not going to get into that right now, so we're just going to focus on wavelength, frequency, and speed. So to start, we're going to look at wavelength. So wavelength is symbolized by the lowercase Greek letter lambda, which kind of looks like this upside down Y, and it is the distance between two consecutive peaks or troughs, or we could say the distance between two corresponding points. And wavelength is measured in meters, usually nanometers, just to put it in numbers that are easy for us to work with. But you can also see other common wavelength units in your book on page 215. You have a nice table that you can look at. When we look at frequency, we can look at it as the number of waves that passes a given point per second usually. So frequency is symbolized by nu, which is a lowercase Greek letter, and in the SI system that we typically use, cycles are understood. So instead of saying 5 cycles per second, we usually would just say 5 per second, and all types of electromagnetic radiation travel at the same speed. So what that means is the shorter the wavelength, the higher the frequency. So if we take a look at this top example, notice that we have a lot of waves. This is a short wavelength, right? This is a very short wavelength, and we have a lot of waves in this given unit of time versus this bottom example where we only have 2 waves in the same amount of time. So this top example we could say has a higher frequency. This bottom one would have a lower frequency. And frequency is measured in hertz, which is the same as per second. So it's very important to know when you see something that says hertz, that means per second. So when we're looking at electromagnetic radiation, it is important to know that all electromagnetic radiation, all, travels at the same speed. And that is this, 2.998 times 10 to the 8th meters per second. That is the speed of light. It is on the equation sheet that you get for the AP test, but it is also very important to know this. We are not using 3.0, we're using 2.998 times 10 to the 8th. So therefore, because all electromagnetic radiation travels at the same velocity, we can actually use speed of light equals lambda times nu to figure out wavelength or frequency. So if you take a look, I want you to look not only at this equation, but also take a look at these pictures, and I want you to make a note of how wavelength and frequency are related. So let's say if you have a high wavelength, what does that mean about frequency? Or what does it mean if you have a short wavelength? What does that mean about frequency? So write that down in your notes as well. So just to summarize our discussion about light as a wave, we can think about a wave in terms of wavelength, which is lambda, and that is distance per wave. And then frequency, which is nu, is the number of cycles per second. And then the relationship, c equals lambda nu. The higher the wavelength you have, if this number is higher, your frequency will be lower because speed of light is always going to be the same. So if one goes up, the other goes down. So when we talk about electromagnetic radiation and wavelength and frequency, it's important to know the electromagnetic spectrum. So this shows you the electromagnetic spectrum, and it shows you the different types of radiation. So we start with gamma, and notice gamma has the smallest wavelength and the highest frequency. And then we have radio, which has the longest wavelength but the shortest frequency. So if you take a look down here at the bottom, this gives all of the characteristics of each side of the spectrum. And each type of electromagnetic radiation has different properties, and the reason that it has different properties is because of that different wavelength. So this shows you the electromagnetic spectrum, but if you also want to see it in your book, it's on page 215, and you have a visual very similar to this. So in the 19th century, physicists thought they had it all figured out. They thought that they knew wavelength, frequency, and they were even discouraging students from pursuing careers in physics because they thought that all the major problems had been solved. But then this idea arose that matter and energy were distinct. And then certain experiments suggested that this was not right. So what that means is wave theory didn't cut it. So a scientist by the name of Max Planck had the first important advance in this new idea that matter and energy are similar. And Planck figured out that light can be released or absorbed by atoms in these chunks. And he called these chunks quanta or photons. So the wave nature of light does not explain everything that scientists were discovering, and Max Planck found this idea called photons. And it was a great surprise because a lot of people thought that energy was continuous, which meant that transfer of any quantity of energy was possible instead of simply smaller transfers. So Einstein actually used Planck's assumption to explain what he found in the photoelectric effect. So the photoelectric effect essentially had energy bounce off of a metal surface and release electrons. And from this experiment, he proposed that energy is proportional to frequency. And so what he said is that radiation can be viewed as photons, and from these photons we can actually calculate energy or frequency. So using this equation, E equals h nu, we can solve for either energy or frequency. So E is energy, h is Planck's constant, which is always 6.626 times 10 to the negative 34th, and then nu is frequency, which is hertz or per second. So this is on the equation sheet as well. You just have to know how to use it. So to see an actual example of the photoelectric effect, you can actually go to this video on YouTube, and you can actually see someone that's performing kind of a simulation of the photoelectric effect and see what the results were and why those are important. So based on the ideas of Planck and of Einstein, what we can actually do if we know the wavelength of light, we can actually calculate the energy of one photon of light. And we can do that by using C equals lambda nu and E equals h nu. And we can actually find the energy of one photon. Now, if we wanted it to be more than one photon, all we actually have to do is just multiply h nu times n, where n gives us our number of photons. So if we have 5 photons, we simply multiply this by 5. So we can actually calculate energy if we're given wavelength. We can use algebra, we can substitute, and actually solve for any of these variables. So another idea that a lot of scientists were continuing to work on was the idea of an emission spectra and what that means. So that is now what we're going to look at with our discussion on energy and wavelength and electrons. So for atoms and molecules, you don't simply observe a continuous spectrum, you actually only see a line spectrum. So a continuous spectrum results when you shine white light through a prism. And a continuous spectrum actually looks like this top example. Looks like the rainbow. And if we were to look through a spectroscope and we looked at the ceiling lights, we would see for the most part a continuous spectrum. However, when an element such as hydrogen gas or even water vapor is passed through a prism, we only see a few lines like these two examples below, and each line has a corresponding wavelength. So we actually use a spectroscope, and this is what we see inside the spectroscope, and this indicates the certain energies that are allowed for the electron in the atom. So in other words, we're able to actually see that the energy of the electron is quantized, which means we can only have certain energy levels when an electron is released. So with the emission spectrum, only certain wavelengths or energies are present in that spectrum. An element's emission spectrum is unique to that element, so it's very much like a fingerprint. So this spectrum is actually released when excited electrons return to lower energy states. So this is when electrons are released. So it's going from higher energy to lower energy. That's actually how we can get this emission spectrum and how we can see it. So based on the scientists that came before him, Niels Bohr was able to come up with what is called the quantum model of the hydrogen atom. And what we're going to look at is we're going to look at his key ideas in this model of the atom. So the first key idea is that electrons are permitted in only certain orbitals that have specific energies. So he said that electrons are found in orbits that surround the nucleus, and they travel at a fixed distance and a fixed speed around that nucleus. So we know Bohr was wrong about the orbits, but let's just pretend that he meant energy levels instead, because that's really what they are. So Bohr said that when an electron absorbs energy, which is called the quanta, that's that certain energy, it can jump up to an energy level that's further from the nucleus. So let's say that it gains enough energy to jump from this first energy level all the way out to, the fifth or sixth energy level. That is what happens when it absorbs energy. But electrons can only move from one allowed energy level to another. Okay, that's because energy is defined by E equals h nu. So the electron could not jump from this first orbital to the 3.5 orbital, right? It can only be in those specific energy levels. And then Bohr also said that when electrons absorb energy to jump up a level, they immediately release the same energy to get back to ground state. So ground state is where the electron started. So if it was at n equals 2, its ground state is n equals 2, and that's where it falls back to. But as soon as it jumps up, it releases that same amount of energy to fall back down to where it was before. So sometimes the energy that is absorbed or released by these excited electrons can actually be seen as different colors of light. And so the color depends on the wavelength or the energy of light that is emitted. So if it is a specific wavelength that's in the visible region, then you'll actually be able to see that in terms of the color. That's actually how we can get the emission spectra for different elements, is that we can see that visible light, and that's how we know that electrons were excited and jumped and fell back down. So probably the most important equation to come from Bohr's model is what is called the Rydberg formula. So this formula that we have here is called the Rydberg formula, and what this formula allows us to do is actually calculate the change in energy of an electron when an electron falls or is absorbed from one energy level to another. So we have delta E, this is change in energy, is equal to negative hc, where h is Planck's constant, c is the speed of light, RH is the Rydberg constant, which are given here, and NF and NI are the final and initial energy levels, respectively. So what this allows us to do is to look at the energy absorbed or emitted when an electron is either excited or is falling back down to ground state. So Bohr actually examined the light that was released by the atoms of certain elements, but he only worked with hydrogen since it had one electron. So when he was examining the light that was released, he used a spectroscope to analyze the light, and he actually looked at the emission spectrum of hydrogen to come up with his ideas on electrons being absorbed or released. So this is actually a diagram or a model of Bohr's model of the atom. And so this is just a diagram for the hydrogen atom. So we can see that we actually have 21 possible emission lines. And that's because we can have atoms, or we can have, electrons falling from n equals 2 to 1, 3 to 1, 4 to 1, 5 to 1, 6 to 1, and then we could also start with n equals 2 falling down, n equals 3 falling down, n equals 4, 5, 6, and 7. So we can actually have 21 possible emission lines, which then means we can also have 21 possible absorption lines. So remember, emission is when the electron is falling to ground state, absorption is when it is excited. So when looking at the possible spectral lines that come out of a hydrogen atom, we actually have what are called different series based on where the electron is falling from and falling to. So we have the Lyman series, which is when we have an electron falling from an energy level down to n equals 1, and this is actually in the UV range. So the Lyman series we actually cannot see because it's ultraviolet emission lines. Then we have the Balmer series, which is when we have an electron falling to n equals 2. This is visible light. So we can actually see the emission of Balmer series because it's visible lines. The Paschen series is when we have an electron falling to n equals 3. This is actually the infrared band. And so because it's infrared, again, we can't see that wavelength, but it is occurring. So these energy differences, again, within each of these series, we can actually calculate using the Rydberg formula. So Louis de Broglie was another scientist that came along after Bohr, and he suggested that an electron that's moving about the nucleus of an atom behaves like a wave. Therefore, we need to make sure it has a wavelength. So he said if light can have material properties, matter should have wave-like properties. And so he said light travels through space as a wave, so therefore it has wavelength, and we can use diffraction patterns to actually look for the electrons. So he proposed that the wavelength of the electron depends on its mass and its velocity. So when we look at the de Broglie equation, we have our wavelength, Planck's constant, and it's dependent on mass and velocity. So mv, when you multiply together, is actually called momentum, so that's a physics term. So momentum is really based on mass. So if you think about it, like a very large person is going to be much more difficult to stop than a smaller person. So larger particles have very short wavelengths because larger particles, if we have here, this is large, this is going to be very small. So very large particles have very short wavelengths, and vice versa is also true. And then we come to Heisenberg. So the discovery of the wave properties of matter actually raised some new questions. Heisenberg proposed that the dual nature of matter places a limitation on how precisely we can know both the location and the momentum of an object at any given time. So he mathematically related the uncertainty in both position and momentum using this equation, which we're not really going to get into this equation, but this is the Heisenberg equation. And what he said is it's impossible to simultaneously know both position and momentum of an electron at a single time. So the more accurately we know the position, then the less accurately we can know the momentum, and vice versa. So there is a lot of uncertainty in finding the electron in an atom. So overall, de Broglie and Heisenberg set the stage for a new and more broadly applicable theory of atomic structure. At first, Bohr's model looked very promising. However, when his model was applied to atoms other than hydrogen, it did not work at all. So his model of the atom does not explain any other atom besides hydrogen, and he said that electrons move in circular orbits, which we know doesn't happen at all. Therefore, it also violates the Heisenberg uncertainty principle. So even though Bohr's model might be useful for us, it actually doesn't explain as well as de Broglie and Heisenberg suggested. And so what we'll actually look at in upcoming videos are actually the quantum mechanical model that Schrödinger proposed, and then we'll be able to have a much better idea of the atom.